AI broke the internet again, and this week has been absolutely insane. Meta releases MuseSpark 1.1, their most capable model yet, with 1 million token context, agentic multi-agent orchestration, full computer use, and some genuinely impressive coding results. Claude Code gets a full browser built into it, so you can open documentation, external sites, and sign into apps directly next to your code. Bonsai launches as the first 27 billion parameter class model that actually fits on your phone, at just 3.9 gigabytes, while still retaining 90% of the full precision model's performance. OpenMOSS releases a genuinely fascinating new 11 billion parameter real-time video model that watches a live feed and speaks, stays silent, or self-corrects mid-sentence as the scene changes in front of it. SenseNova releases a 7 billion parameter model that handles detection, depth, segmentation, normals, and multi-view 3D geometry all in one model without any task-specific heads. StepFun releases StepEdge, a full family of multimodal models built for phones and cars, hitting tool call latency under 100 milliseconds on device. Nvidia publishes ARDY at SIGGRAPH 2026, a real-time human motion generator that lets you steer a character with a text prompt mid-animation or a mouse waypoint, all while keeping full kinematic constraints over long horizons. And 1X Technologies reveals Enio's new 25 degree of freedom tendon-driven hands, which they are calling the most capable robot hands ever built, and a lot more. So let's jump right in. First up, Meta releases a pretty significant new model this week. It's called MuseSpark 1.1, and this is the latest model from Meta Superintelligence Labs, building directly on MuseSpark with major improvements across agents, computer use, and coding. And for the first time, developers can now actually build with it through the new Meta Model API, which just launched in public preview. Now, the three headline capability areas are agents, computer use, and coding. Let me break each one down. On the agentic side, MuseSpark 1.1 has a 1 million token context window that it can actively manage itself. It remembers prior actions, retrieves relevant information from earlier in a long workflow, and compacts its context to keep the critical steps available for later. It also zero-shot generalizes to new native tools, MCP servers, and custom skills without needing to be specifically trained on them. It also handles multi-agent orchestration directly. As the main agent, it gathers context, makes a plan, and delegates parallel subtasks to subagents to optimize end-to-end latency. As a subagent, it adheres tightly to its assigned job and knows when to escalate back to the main agent. On computer use, it can handle complex multi-app workflows where information keeps changing on the fly. And instead of reasoning through every desktop step one click at a time, it knows when to write a script for automation, when to just click directly, and generates batches of actions at each step rather than one at a time. For a concrete example, they show it reorganizing a dinner party order mid-task when new context arises without any user intervention. And they also show it building a full Facebook Marketplace listing from a video shot on a smartphone, operating the browser entirely on the user's behalf. On coding, it can diagnose and fix complex bugs in real enterprise code bases, implement new features, and run large migrations. On Meta's internal coding benchmark, it significantly improves over the original MuseSpark. Replit's CEO specifically called it a complete agentic foundation, naming the combination of million token context, multimodal support, built-in search, parallel tool calling, and competitive coding ability in a clean, open AI-compatible package. Now, for your reference, there are no external public benchmark numbers in this announcement. The evaluation report is linked, but the comparisons are internal only. So these are all Meta's own claims. What I can say is that early partner companies, including Replit, Klein, Box, and OpenClaw all have their own quotes about it in the release, which at least suggests real-world usage has validated some of the claims. MuseSpark 1.1 is live now in the Meta AI app in thinking mode on meta.ai, and the Meta Model API is in public preview for developers starting today. If you're interested in reading further, I'll link to this page in the description below. Also, this week, Claude Code gets a pretty useful new feature. They've added a full browser directly into Claude Desktop's Code tab. Now, the browser in Claude Code isn't just a preview pane for your running app. It's a tabbed browser. You can open documentation, external sites, issue trackers, or basically any website right next to your code. No more alt-tabbing between your editor and a browser window. The way it works is you press CMD plus Shift plus B on macOS or Ctrl plus Shift plus B on Windows to open it, or select it from the Views menu. When Claude links to an external page in chat, a chooser appears offering to open it in the built-in browser or your system browser, and you can sign into sites directly in the pane, including Google, OAuth pop-ups, and other login flows. Now, Claude can also interact with external pages using the same tools it uses to verify your app. But there are two important safety checks in place. Safety classifiers review every write action Claude takes on external pages, like clicking and typing, regardless of what permission mode you're in. And in most modes, a domain allowlist check also applies before Claude navigates to a new external site, so you get a prompt the first time it acts on any external domain. Now, this is a Claude code feature, not a model update, so it's available across all plans that have access to the Code tab in Claude Desktop. If you're interested in reading further, I'll link to this page in the description below. Next up, we have a genuinely exciting new open source model release. It's called Bonsai, and this is a 27 billion parameter class model from PrismML that comes in two variants, a 5.9 gigabyte ternary version and a 3.9 gigabyte 1-bit version. And that 1-bit version is the first 27 billion class model to actually fit on a phone. Now, you see, the problem with running a 27 billion parameter model locally is the memory footprint. In 16-bit precision, it takes 54 gigabytes. Even a good 4-bit build lands at 18 gigabytes, which is way too large for a phone and too large for most laptops. Bonsai 27B solves this with something they call ternary and 1-bit quantization, which is different from the kind of 4-bit or 8-bit quantization you usually see. In ternary mode, every weight is literally one of three values, -1, 0, or +1. That gives 1.71 effective bits per weight and a 5.9 gigabyte footprint. In 1-bit mode, every weight is either -1 or +1. That gives 1.125 effective bits per weight and a 3.9 gigabyte footprint, small enough to run on an iPhone 17 Pro within the roughly 6 gigabytes of memory a phone app can actually access. Now, the really impressive part is how much capability you retain at those sizes. Here are the benchmark numbers across 15 tasks, evaluated in thinking mode. The full precision baseline scores 85.0 overall. Ternary Bonsai 27B scores 80.5, retaining 95%. 1-bit Bonsai 27B scores 76.1, retaining 90%. Breaking that down by category, math is nearly untouched. 95.3 full precision, 93.4 ternary, 91.7 for 1-bit. Coding, 88.7, 86.0, and 81.9. Agentic and tool calling. 80.0, 74.0, and 66.0. That tool calling drop on 1-bit is worth noting if you're planning on running agent workflows. For comparison, the most aggressive conventional 4-bit build of the same base model scores significantly lower than 1-bit Bonsai 27B while occupying 2.5 times more memory. In terms of speed, it hits 163 tokens per second in 1-bit and 134 in ternary on an RTX 5090. On an M5 Max, it reaches up to 87 tokens per second in 1-bit and 58 in ternary. The model comes with full multimodal support, including vision, a 262K context window, and speculative decoding. It runs natively via MLX on Apple devices and via CUDA on Nvidia GPUs through custom low-bit kernels. The awesome thing is they've released this already under Apache 2.0. Weights are on Hugging Face, the code and demos are on GitHub, and there's a free limited-time developer preview API if you want to test it without downloading anything. If you're interested in reading further, I'll link to this page in the description below. Also, this week, OpenMOSS releases a really fascinating new open source video model. It's called MoSVL Realtime, and this is an 11 billion parameter model that fundamentally changes how AI interacts with a live video feed. Now, you see, the problem with basically every video AI model right now is that they work in offline mode. You record a video, finish it, upload it, and then the model answers, which is fine for reviewing footage, but completely useless if you need something to happen in real time. MoSVL Realtime solves this by working in what they call the present continuous tense. It watches a live feed and makes three kinds of decisions continuously. Anytime response, if you ask a question at any moment, it answers based on the current frame without waiting for the video to end. Proactive silence. If no key events are happening, it stays quiet on its own without you having to tell it to stop talking. And timely correction. If the scene changes after it's already started answering, it updates its response mid-sentence. The classic example is counting people in a room while someone walks in. Now, how this works is really elegant. Rather than having separate systems for watching and for speaking, video frames, user questions, and model answers are all woven into a single interleaved token sequence. A question comes in like a live chat message, inserted at any point in the timeline. And a special silence token lets the model explicitly decide to stay quiet during any given generation step, rather than forcing it to keep producing text. The architecture uses decoupled cross-attention to separate video feature extraction from text generation for speed, absolute timestamps on every frame so the model understands physical time independent of frame rate, and a new positional encoding system called XROPY that handles both spatial and temporal dimensions uniformly. Here are some of the demos. You can see it watching surveillance footage of a snowy street, staying silent while nothing happens, and instantly alerting the moment someone falls. You can see it live commenting a football match with professional TV commentary tone, catching every pass and shot in real time. And you can see it transcribing a person writing out math equations on a whiteboard, updating the transcription line by line as each new formula appears. On streaming video understanding benchmarks, it achieves open source state-of-the-art results and specifically leads on proactive speaking metrics, which is the hardest part to get right. The awesome thing is they've released this already under Apache 2.0. The model weights are on Hugging Face and the code is on GitHub. If you're interested in reading further, I'll link to this page in the description below. Next up, we have a pretty impressive new open source computer vision model. It's called SenseNova Vision, and this is a 7 billion parameter model from SenseNova that handles 10 different computer vision tasks in one unified architecture, with no task-specific heads or decoders at all. Now, you see, the traditional approach to computer vision is to build separate specialist models for each task. One model for object detection, another for depth estimation, another for segmentation, another for surface normals, and they each use their own custom output heads and loss functions. SenseNova Vision replaces all of that with a single model that takes a natural language instruction and generates either text, an image, or a mix of text and image as output, depending on what task you're asking for. So for detection, it generates bounding box coordinates as text. For depth estimation, it generates a depth map as an image. For segmentation, it generates a binary mask. For camera pose estimation, it generates structured camera records, all from the same model, all through the same interface. Now, for the benchmark numbers. On object detection, it ties for first on CocoCom at 56.6 mph, matching grounding DynoSwin T. On dense small object detection, it leads at 66.8, ahead of locate anything at 58.7. On depth estimation on UV2, it hits 98.1 delta 1, matching depth anything V1, but doing so while also handling every other task. On referring segmentation on RefCoco, it scores 81.3, and on reasoning segmentation, it leads at 63.2. On multi-view geometry, it's competitive with Depth Anything 3 and VGG8 on most tested splits. Now, I'll note the license here. SenseNova Vision is released under CC BY NC 4.0, which means it's free for research and non-commercial use. Not Apache 2.0, so double check before using it commercially. Can you run this on a consumer GPU? At 7 billion parameters? Yes. You need a GPU with enough VRAM for a 7B model. The model uses standard Hugging Face transformers, so an RTX 3090 or 4090 with appropriate quantization should work. If you're interested in reading further, I'll link to this page in the description below. Also, this week, StepFun releases a pretty ambitious new model family. It's called StepEdge, and this is a full family of multimodal models built specifically for running on edge devices like phones and cars, not cloud servers. Now, the family follows a 1+N architecture. The core is a single text and vision-based model. Connected to it is an audio module, a GUI agent module, and an image generation module, each specialized for their tasks but all running locally. For the base text and vision model, the benchmark numbers put it competitive with Qwen 3VL4B and Gemma 4E4B across image understanding, OCR, and spatial reasoning. On 12 different evaluated tasks, it takes the top or second best spot on most of them against same-size competitors. On the GUI side, it beats Claude Haiku 4.5 on OS World Verified for computer use tasks, which is a pretty notable comparison given that Haiku is a cloud model, and it handles real-world phone apps like WeChat, Xiaohongshu, and TikTok in their mobile agent benchmark. On audio, the ASR accuracy hits a Chinese character error rate of around 3.1% and an English word error rate of around 3.6%, which is actually close to specialized ASR model territory, not just a general VLM doing audio on the side. And for inference speed on an NPU, it handles a 1024 token text input in about 4.33 seconds, a 768 resolution image in about 5.61 seconds, and a 30-second audio clip in about 10.72 seconds, and tool call latency as low as 100 milliseconds for local agentic workflows. Now, I'll note these are internal self-reported benchmarks from StepFun, not an independent evaluator. And not all model weights appear to be publicly available yet, so check the project page for the latest on access. If you're interested in reading further, I'll link to this page in the description below. In humanoid robot news, Nvidia publishes a really impressive new motion generation model at SIGGRAPH 2026. It's called ARDY, which stands for Autoregressive Diffusion with Hybrid Representation for Interactive Human Motion Generation. And what makes this one genuinely exciting is the real-time interactivity. You can steer the character mid-animation using a text prompt, mouse waypoints, kinematic constraints, or full-body keyframes, and the motion updates smoothly and immediately without stopping to regenerate from scratch. Now, you see, the problem with existing motion generation tools is a trade-off between quality and speed. The best offline models like Komodo produce really high-quality, controllable motions, but they're too slow for interactive use. The real-time models are fast, but they sacrifice controllability and struggle with long horizon goals. ARDY is designed to bridge this gap. So how this works is it uses a hybrid motion representation that combines explicit global root motion, which gives precise scene space control, with a compact latent embedding of body motion, which makes the generative learning more efficient. Then, an autoregressive two-stage transformer denoiser first predicts the root motion, then conditions on that to predict the body motion. These two stages run in an interleaved way that maintains fidelity, even as you keep injecting new text prompts or kinematic constraints during generation. And crucially, those kinematic constraints can be set way ahead of the current generation window, so the model plans toward future waypoints while still producing smooth motion in the present. That's what they mean by long horizon goal reaching. Here are some examples. You can see a character walking and limping and doing a victory dance, all in response to successive text prompts typed during live generation. You can see path following where a route trajectory is drawn in 3D space and the character moves along it. Full body keyframe constraints where you specify a pose far in the future, and the model generates smooth motion arriving at that pose. And interactive humanoid robot control, combining ARDY's real-time motion generation with Nvidia's sonic physical tracking policy on a Unitree G1 robot, steered with mouse waypoints and keyboard commands. The awesome thing is they've released the model and inference code already on Hugging Face and GitHub. If you're interested in reading further, I'll link to this page in the description below. And finally this week, 1X Technologies reveals the new hands for their NEO humanoid robot, and these are genuinely impressive. They're called NEO's hands, and these are 25-degree of freedom tendon-driven hands that 1X is describing as the most capable robot hands ever built, matching or surpassing human hands across the dimensions that actually matter for real-world manipulation. Now, you see, the reason dexterous robot hands are so hard is that most of them are essentially write-only devices. You command a position, the hand goes there, and nothing meaningful comes back. The reason is the gear ratios. Standard robot hands use gear ratios of 101 or 201, and at those ratios, friction swallows the contact forces before they ever reach the motor. The hand is numb through its own joints. NEO's new hands run on quasi-direct drive tendons at low gear ratios of approximately 5:1 to 15:1. All 25 degrees of freedom, 22 in the fingers, and palm plus 3 at the wrist are natively force-controlled and fully back-drivable, which means when you push on a finger, it yields and also reports exactly how hard you pushed. Force flows out and information flows back through the same physical path. They call this force transparency, and it turns every grasp into a measurement. Now, here are the actual specs for your reference. Peak torques reach 3.5 Newton meters at the thumb CMC joint and 2.6 at the finger MCP joints. Distal flexion force up to 45 N. Wrist torque up to 17.75 Newton meters. Positioning accuracy of plus or minus 0.2 millimeters. And the hands are IP68 waterproof and food safe, so NEO can literally wash its own hands at the sink. They also include rich tactile sensing across the fingertips that measures normal force, contact location, and shear. So the robot can detect when an object is starting to slip and respond in real time before it finishes dropping. Here are some of the demos. You can see NEO assembling Lego structures. picking individual screws and coins from a wallet, plugging in a USB-C charger, zipping a jacket, pouring tea from a kettle, catching a squishy ball, and sorting grapes by color. As you can see, the precision and adaptability across all of those is actually ridiculous for a robot hand. And the production context here is actually the most important part. 1X says hundreds of these hands have already come off their production line, and they're targeting 10,000 hands produced this year. These are the hands that will ship on every Neo going forward. These hands aren't open source hardware, but the detailed engineering breakdown and all the demo footage is on the 1X website. If you're interested in reading further, I'll link to this page in the description below. And that sums up all the highlights in AI this week. Let me know in the comments what you think of all of this. Which piece of news was your favorite? And which tool are you most looking forward to trying out? As always, I will be on the lookout for the top AI news and tools to share with you. So if you enjoyed this video, remember to share, subscribe, and stay tuned for more content. Also, there's just so much happening in the world of AI every week. I can't possibly cover everything on my YouTube channel. So to really stay up to date with all that's going on in AI, be sure to subscribe to my free weekly newsletter. The link to that will be in the description below. Thanks for watching, and I'll see you in the next one.